Hello, my name is Charlie.
And my name is Zach, and this is our presentation on motion in space. So vectors play a huge role in the content we cover in Calculus 3. And a vector is defined as a quantity having direction as well as magnitude, especially in determining the position of one point in space relative to another. So vectors are written in the following forms. The first one is for 2 dimensions, and the second one is for 3 dimensions, and the images on the right display vectors in both 2D and 3D on graphs.
So in using vectors, we have talked about something called vector-valued functions. Vector-valued functions are functions that describe the path of motion of an object using an input, which is usually t for time. You write a vector-valued function as r of t equals x of t, y of t, z of t. Vector-valued functions can be looked at as 3 different equations that each solve for a component of an individual point on the graph, or it can be looked at as a function with 3 dependent variables that graph out the function. 3 components that make up the vector represent the head of the vector, which is used to represent the curve. As you can see on the left, we have a little graph of the vectors pointing to the head, which are the points on the curve of the graph.
As with most normal functions, you can apply calculus to vector-valued functions as well. This means you can derive and integrate them. This allows us to use vector-valued functions to perform calculations on an object in motion. So as you've learned from previous courses, the derivative of position is velocity, and the derivative of velocity is acceleration. And you can use those same ideas when working with vector-valued functions.
So we made an example. I'll just go ahead and read it out. So a small rocket is fired from a launch pad 15 meters above the ground with an initial velocity of 150, 250, 350 meters per second. A crosswind blowing to the north produces an acceleration of the rocket of 4 meters per second squared. Assume the x-axis points east, the y-axis points north, and the positive z-axis is vertical and the ground is horizontal. So the acceleration acting on the rocket is the wind in the horizontal and gravity in the vertical. So at a of t equals 0, 4, negative 9.8. We can find the antiderivative of acceleration to find the velocity vector. So by taking the integral of acceleration, we will find 0, 4t, negative 9.8t plus c. And when you take the integral of a vector, it's like taking the integral of 3 individual equations. So it is given that v sub 0, velocity of 0, is equal to 150, 250, 350. So by substituting it into the antiderivative above, we find that v sub t is equal to 150, 4t plus 250, negative 9.8t plus 350. So we can now integrate the velocity vector to find the position vector. And so when we integrate velocity, we find the position vector is going to be 150t, 2t squared plus 250t, negative 4.9t squared plus 350t plus c. So it is given that r sub 0, which is the position, is equal to 0, 0, 15. So by substituting it into the antiderivative above, we find that r of t is equal to 150t, 2t squared plus 250t, negative 4.9t squared plus 350t plus 15. Using the position vector and the velocity vector, now we can answer those other questions.
So how long is the rocket in the air? The rocket hits the ground when the z component of the position vector, or the height of the rocket, equals 0. To find this, you just set the z component of the position vector equal to 0, which results in t equals 71.47 and negative 0.04. Since time cannot be negative, the rocket was in the air for 71.47 seconds. When does the rocket reach its maximum height? To find the maximum height of the rocket, we must first find where the vertical component of the velocity equals 0. By solving for t, this results in t equals 37.71 seconds. We can then plug this into the z component of the position vector, which equals around 6,265. Therefore, the maximum height of the rocket is 6,265 meters.
So yeah, that's how you solve our example. Thank you for listening to our presentation on motion in space.